1145, right? Instead of OS, you will have MFP at 1145. Right? So let us continue with the OS. So we were discussing the concept of relocation, right? Relocation means you shift a process as and when required, right? So in which kind of partitioning methods relocation becomes necessary, right? So that's what we'll discuss first, and then we are going to go for the important topic, as I said, that is paging, right? So let us start with the first case. If you go with equal size fixed partitioning, right? Now, if you remember, fixed partitioning divides your memory into, you can say, same size memory chunks, right? And equal size fixed partitioning means size of every chunk will be same. Okay. So when you go with this method, do you remember what was the placement algorithm that we used? Yes. What is the placement algorithm for equal size fixed partitioning? Is it necessary to select a partition in this case? That is another way of asking this, right? Is it necessary to select a specific partition for this case? The answer is no, right? Because size of every partition is same, right? So you can load your process anywhere, okay? And when the term anywhere comes, right, which concept will come into picture? When I say that I can load my process anywhere, which concept will take place? Relocation, isn't it? Are you able to understand this? At least those who are present, right? Please answer. Yes, okay. Body is equal size partition. Okay, you can say that, Priyank. That's correct. I'll explain, right? Why? Right? So why do we need to use relocation over here? So suppose you assume, Sainish, that if we are having three free partitions, free partitions, and all of them are of, let us say, 4 MB, right? And if you are getting a request of size 3 MB, right? Now, are you going to select which of the 4 MB partition you will be allocating the process? The choice is trivial over here, isn't it? I can allocate anyone out of the 4 MB partitions. Agreed? Right? So, if your OS allocates the first 4 MB partition, or in some other scenario, your OS allocates the third 4 MB partition, that does not matter, isn't it? Do you agree with this, Sainish? So, due to that, your process might be loaded either in the first 4 MB partition or in the third 4 MB partition, right? So, ultimately, it has to relocate, isn't it? It has to change its memory location. Fine. So, that is why equal size fixed partitioning requires relocation. Clear? Right? Partition depends on OS, definitely. And it depends upon memory size also, right? Because what kind of memory arrangement you are having, right? That also decides this factor, right? Next is, yes, okay, unequal size fixed partitioning. If you go with unequal size fixed partitioning, right? So partition is still having a boundary. That means size of the partition is fixed, but you will divide your memory into different size partitions, right? Like you will allocate, you will allow a partition to be of 2 MB size, some will be 6 MB, some will be 8 MB, and so on, right? Remember that concept, unequal size fixed partitioning, right? And another thing is, if we are using single queue per partition, let me just go back to that slide so that you all can just recall, right? That will be better. Yes, this one. If I am going with the right-hand side approach, right, then what will be the concept? Yes. If I am going with this approach, relocation will be required or not? If you are going with single queue per partition, right? Your process can be loaded into either over here, or either over here. Agreed? Yes or no? Right? Process can be loaded into any of the available partition, right? And when again any word comes, right? Which concept applies? Wherever you find any, right? Any means you have multiple options to choose from. That is going to have occurrence of relocation. Exactly, right? I hope all of you are able to understand, right? First and second cases clear, right? If you might be asked objective, let us say, which of the following situations lead to relocation, right? You are given 5 options. You need to pick the correct one, right? You should be able to do that, right? In GATE, this kind of MCQ can be asked, right? So you should be knowing this, right? Okay, let us continue with the third case. The third case says that we are having dynamic partitioning. Now it is very obvious. In case of dynamic partitioning, where do we allocate the process? Wherever the smallest wastage is there. Yes or no? Wherever smallest wastage is there. Now sometimes your process request is, let us say, 2 MB, right? And earlier when you allocated that process, there was a 3 MB partition available, right? Sorry, there was a 3 MB partition available. So you will load your process into 3 MB partition for the first time. Now, when the process goes out, when it is swept out, at that point, 3 MB partition is not free when you load it again, right? So when you load it again, you have one option, let us say 4 MB, right? So you have to go with 4 MB in this situation. I'll repeat. Your request is 2 MB. Earlier, you allocated a 3 MB partition for that, right? Fine. So there was a 3 MB space available. Out of that, you allocated the 2 MB space. That is what we have in dynamic partitioning. Okay. Now, after the process is swept out, okay, that 2 MB which was allocated is now occupied by some other process. So when you bring the process once again, is the location of process going to change if the previous location is occupied? If the previous location is occupied, it will change, definitely. So what is that concept again? Relocation. Clear? 3 approaches, right? Okay, I'm going with the fourth one now, compaction, right? It is obvious that compaction means you are going to merge the processes together. And when we are merging the processes together, what is going to take place? Change of addresses, and change of addresses means relocation. Yes? Clear with the 4 cases, right? So these 4 are the situations, yes, where wastage is low, there we use dynamic means how. Okay, dynamic basically means, Sainish, if you remember, yes, I'll answer both the equations. Let us first look at the dynamic partition part, right? In case of dynamic partitioning, if you remember, what was the process we use? We look at the available space, right? We look at the available space, and suppose your request is 14 MB, right? So your available space is 36 MB. You divide that into 2 parts. One will be 14 MB, and the remaining will be the free space, right? So in case of dynamic partitioning, we don't have internal fragmentation, right? So that is why wastage would be low, we can say, in terms of internal fragmentation. But there can be external fragmentation. Tainish, remember that? Okay, fine. Highest relocation frequency will be there in compaction, obviously, yes, right? But that depends upon how frequently you do relocation. If you are not doing relocation frequently, then it will remain similar, you can say, not same, right? But in ideal scenario, relocation is required very frequently because you are having continuous flow of processes going in and out, right? So relocation is being done, or compaction is being done very frequently. So yes, I agree with your point, right? If here one process needs more size, then it has to relocate. In which case you are talking? Dynamic partitioning, Vishruth? Process 1 needs more size. Yes, in C figure. Exactly. That is one point we have not discussed, but that is true. If process 1 requires extra space, you have to shift out P2. Because what is required in case of dynamic partitioning? Memory allocation has to be contiguous. You understand what is contiguous memory allocation, right? Contiguous means sequential, right? So it will be swapping. You have to swap out P2, right? Give extra space to P1. Okay, then if still space is there, you bring P2 again, right? So a lot of dynamic decisions have to be taken when you are going with this dynamic partitioning, and that is why paging is a better option, because paging takes away this restriction, right? In paging, we don't require to load the process in sequential locations. You can load it anywhere, wherever the free space is available. We'll see that very soon, right? Okay. So Vishnu, are you clear with that point? Okay. In dynamic, it can divide as per the size of process. Yes, that is why it is dynamic. That's correct, Sainish. At runtime, you decide, right? That is why it is called dynamic partitioning. Okay, fine, good. So now let us continue with this relocation. So this was just a concept where we defined where relocation is required. Okay. So what is the summary of all these points? Physical memory references of a process are not fixed. That means where it will be loaded physically, that is not fixed. Okay. And this is going to be managed by the concept of addressing, right? How this mapping occurs is going to be managed by a concept that is known as addressing, right? And this is the reason why OS designers have come up with 3 types of addresses. That is what I'm going to cover next, right? So the first type of address that is defined in the OS is called physical address or absolute address, right? It is the actual location in main memory, right? Suppose you are having a 500H location, right, in your main memory, right? And if you are pointing to that directly, that is your physical address. That is your actual address, right? But to make the system dynamic or to behave in a dynamic manner, CPU always relies on either a logical address or a relative address, right? So whenever a process is loaded, remember, I am just saying an important statement. Whenever a process is loaded, the addresses which are there in the program are always in form of logical or relative, right? Why so? Because if you, is it guaranteed that you will be getting the same physical address always? Is it guaranteed that you will be getting the same physical address always? No. That is why all the memory references, when you load a process in main memory, are either in logical form or they are in relative form, right? In most of the cases, it is in relative form. We will see what is the difference, right, with an example later on, okay? So what we require at runtime, are you getting some idea? If you are having, or if you encounter a jump instruction, right, in your program, and that jump instruction is currently having a logical address or a relative address. So what we need to do to actually reach that desired location, we have to convert either the logical address or relative address into physical address. Exactly, that is known as translation, right? This concept we are going to discuss in very detail, right? Address translation. We have to convert the logical references or relative references into the actual references so that we can point to the actual data, right? And that mapping is done by your memory management unit, or you can say address translator. We have a separate module in your OS, right, that manages this thing, okay? Let us now look at the definition of logical and relative. Then we are going to look at the example in paging, right? So you will be clear with this. Logical is reference to a memory location, right? It is a reference to a memory location independent of current assignment. That means it is such an address which is existing in concept only, right? It is just existing in concept, right? But it has to be mapped to a physical address if you want to get the actual information. It has to be mapped to a physical address if you want to get the actual information. Second important point, who generates logical address? It is the CPU's job. Whenever process is created, right, process will be created in form of logical addresses, right? You will not be having physical addresses, right? Later on at runtime, CPU hardware and OS will convert that logical address into physical address, right? Okay. Now what is relative address? Relative is a special type of logical address. It is a special type of logical address where address is expressed as a location relative to some known point. Right? So suppose when you load a process, let us say in main memory, will you be knowing the beginning of the process location, or where it is located, or where is the start pointer of that process? Will you know that or not? I'll repeat my question. When you load a process in main memory, will you be aware that what is the starting location of your process? Obviously, yes, right? Why? Because when you will be loading, right, you know what is the starting address where the process is beginning, right? As well as what you will know, upper bound and lower bound, both. That is, what is the ending address? Yes or no? Fine. So if I'm knowing my starting physical address, right, and if I'm knowing my logical address, right, how can I find the actual physical address? Suppose my starting address is 50H, right? And if my logical address or relative address, let us say, is 500, right, generated by CPU. So how will you reach the actual address? 50 plus 500? Yes or no? Are you following this? Right? So you have to add your starting physical address with your logical address. That is how you will be getting what? Physical or absolute address. This is an important point to understand, right? Because entire paging concept is based on this, right? This mapping. Okay, don't worry. We are going to look at some diagrams and examples. Okay, so you'll be thoroughly clear with this. Are you clear with the definitions? Yes? So again, I'll repeat the difference. Physical is something which is actually present, right? Logical and relative are not actually present. They are generated by CPU when the process is created. Fine. And ultimately, we have to convert either logical or relative to the physical address, right? And that is done by your CPU hardware and OS, right? Okay, let us continue with this. So as I said, we have to convert, right? So for conversion, there are two steps. So for a system with relative addressing, address translation is done in 2 steps. The first step is load. Load means what? Load the process in main memory with all the references in relative form. So if you are jumping at some location, that location will be in logical form or relative form, right? Second step is calculate. Calculate the physical address when the instruction or data with relative address is encountered. So when this calculate step will be carried out? At runtime or at compile time? Yes, as a programmer, what you can answer? It is at runtime, right? Because when you execute that process, if you encounter such an address, which is a relative address, you have to convert that into a physical address, right? Yes, that mapping is a costly operation, right? But that is required. Because if you don't do this, relocation is not possible. Yes or no? Right? This is a compulsory concept, right? If you want to achieve relocation, you have to do mapping. Okay, there is no other option, right? Okay. So how do we achieve this, right? We'll look at the diagram first. That is going to give you a better idea, and then we'll look at the theory, right? So suppose you are having 2 registers, right? One is called base register, right? Another is called bounds register in CPU, okay? Base register is going to maintain starting physical address, right, of your process. Base register is going to maintain starting physical address of your process. Then obviously, what bounds will be containing? The opposite part, that is ending physical address, right? So if I know my boundaries, right, based on that, can I convert my address? Yes or no? Right? So let us see how this happens, right? Given a relative address as input, right? You can see that over here. You will be performing an adding operation. you know, you have a adder circuit, right, in your CPU. So adder will be adding two addresses, base with relative, right? What you will get? Absolute address, yes or no? Are you clear up to this? Right? Okay. Now, why we need a comparator over here? Why we need a comparator over here? Can anyone explain? You have seen this kind of diagrams in microprocessor basics, right? I think it should be easy to interpret. Base address is logical address? No. Base address is physical address, as I said. It is starting location of your process. So it is a physical address, right? And we know that in advance because we know from where the process is starting. Clear, Ronak? When you load that process, OS knows the location, right? That's why it is a physical address. Okay, so can anyone tell me why comparator is required? Exactly, to check whether you are going out of bound or not, right? And what is your bound in this case? Ending location or ending physical location of your process, right? Why we are checking this? Because we have seen the concept of security, right? We should not enter the area of kernel, neither we should enter the area of other process, right? That is why this comparison is required. Okay, so we will compare after adding the physical address generated. Yes, that's correct. We are going to come to that point, right? I'll again repeat the process as well, right? So you will be clear. Okay. So comparator will compare the physical address that is generated with the boundary, right? Now the absolute address and bounds content, both are physical or not? Absolute address that we have generated by adder plus the bounds registers content, both are physical addresses, yes or no? Yes, right? So we are comparing that whether we are going out of the boundary or not. If you are going out of boundary, what we need to do? You can see that over here, generate an interrupt. That is alert your OS, right? That this process is trying to cross the boundary, right? So it should stop it immediately, right? To attain the security requirement. Clear up to this exception part, right? Okay. Otherwise, what will do? Otherwise, what you have, that is absolute address, right? That is your actual location which you are looking for, right? So this is the actual location that you are looking for, and that is how you will be able to fetch your data. What the concept? How the mapping occurs, right? This is called address translation, and why it is known as hardware support? Can anyone tell me? Or why do we require hardware support for address translation? Yes, because we require CPU registers, base register and bound register, plus we require adder and comparator, right? That is a part of hardware. That is why it is the hardware which is playing an important role over here, right? So your hardware should be capable enough to perform this computation very quickly. If it does not do, the process will slow down, right? And that is why you are having your hardware being upgraded from time to time, right? This is one of the reasons, because you have to do a lot of computation in background, right? Just for what? We are doing all this exercise just for what? Just for knowing one location, isn't it? Now imagine you are having 10 jumps in your code, right? So what is required for all those 10 jumps? 10 times this process has to be done. So I think we should appreciate the complexity of CPU and the hardware, right? How it is efficiently working and how we are able to fetch the details. I hope you agree. Yes? Yes? Yes. Why we are maintaining bound address? Because bound address is known to us, right? Whenever, as I said, whenever you load a process, at least which two things you are knowing in advance? What is your base? What is your bound? Right? Other addresses you are not knowing in advance because they are dynamically decided. They are in logical form. They are in relative form. That is why what we know, based on that we decide. Is that fine, Rishi?
Using PCB for base address. Right?
It is not PCB. It is pointing, see, it is pointing to the starting location of your process. It is not PCB. Look at this location. It is starting address of your program, right? PCB is at the top, right? This is the PCB part. You can see this, right? Where we are pointing just after PCB. And your process image contains 4 parts: PCB, program, data, and stack. And if you want to start execution, where your pointer should be pointing? At program, the first line of the program. And that is what we store in base register, right? And the end part is where? It is the stack, right? Because your process ends at the stack level, right? So this is the complete boundary, right? This is the complete boundary of your process. Is that fine?
But sir, we are using both starting address and ending address to calculate the final physical address.
Yes, yes.
So rather than fetching starting address from program and fetching ending address from stack, why don't we use a common data structure to store both together?
Can be done, can be done. But this is, you can say, this is a benchmark diagram. Just to explain, you can make this process dynamic. You can make it much more efficient, right? I agree with your point, right? But yes, see, we have to learn a concept from base, right? So this is the basic diagram that we have. It started with this, and now it has been optimized in current situation, right? So in newer operating system, what you are saying has been implemented, right? Okay. So this is the concept. Now let us go to theory. I'm going with the reverse approach, right? We'll revise everything through the theory part, right? What is base register containing? Starting address of the process. Remember, it is physical address, right? Now you should be able to differentiate between the physical address, logical address, and relative address, right? Keep those 3 addresses in your mind, right? Second is a bound register that is maintaining the ending location of the process. That is nothing but the end of your stack, right? Okay. These values are set when? This is important point. These values are set when the process is loaded or when the process is swapped in. Do you understand this point? Until that point, there is no point of loading the registers, right? Unless you have a process in main memory, right? There is no point in having these values, right? So after your process P1, let us say, it is loaded inside in main memory, you store a value of starting address into base register, you store the ending stack address into bound register. Is that fine? Right? And wherever it is swapped out and swapped back in, do we have to rework the same task? Do we have to repeat the same task? Yes, because it is possible that the process is loaded at a different location, right? It was not loaded at the same location. So the same process has to be repeated. Yes, a lot of complexity goes into the background, but your hardware is capable to handle this. Your CPU is, that is why becoming faster and faster, because it has to manage all these things, right? Okay. Now let us see the process. When a process is assigned running state, remember, when a process is assigned running state, the base register will be containing what? Starting physical address of the process, as we said, right? Unless the process starts running, we don't maintain, right? We keep the base register free, right? So if you have only one base register, there is going to be a competition, isn't it? Because whichever process that is going to get running state is going to get the base and bound register. And CPU only contains one base register as well as one bound register, right? If you want to have parallel computation, you need to go with multiple base registers and multiple bound registers, right? So in newer CPUs, they might have come up with that concept, right? If you look at the CPU architecture, you might get some idea with this, right? Okay, I'm not going into that detail right now, okay? Bound register is loaded with ending physical address, right? Now, when the translation occurs, that is this point, whenever a relative address is encountered in your program, the value of base register is added to relative address, right? And what that gives you? Absolute address. Are you clear with this summation? Base plus relative is equal to absolute, right? That is the equation that we have, okay? Now, what check we need to make after generating the absolute address? Let us just refresh. We need to compare with the boundary. Yes, right? So resulting address is compared with the value of the bound register, right? If it is not within bounds, interrupt is generated, right? And that is how OS will come into picture. right? Okay. There are any other processes running, then how we can get the starting address? Shinish, we have only one process in running state at a time, right? We have only one process at a time because we are from starting we have assumed one thing, right? That is, we are going with uniprocessor system, right? So you always know the starting and ending address for that process. Clear? Yes. Okay. Now, this mechanism supports protection. Protection means if you check this, right? Why we are making this check? So that we don't cross the boundary. So that we don't cross the boundary, right? And that is known as a protection mechanism, right? Okay. Fine. Are you clear with this address translation? Right. Now I'll go with paging, right? Okay. Let us start with paging now. We have enough time to go with the basics today, right? If you look at the paging, it is just like fixed partitioning, right? The only difference is the size of partitions will be very small. In fixed partitioning, the sizes are ideally around 4 MB or 8 MB. Yes, yes. Which process? Address translation? Yeah. So I'll again repeat. Whenever you are encountering a jump instruction that is having a relative address, let us say 50H, right? Now that 50H is not a physical address. Agreed, Urjit? So we have to convert that to a physical address. How do we do that? We always know the starting physical address of the process that is maintained inside the base register, right? So that physical address will be added with the relative address, right? And when you add a physical address with relative, the equation is going to give you physical address again. And that is nothing but your absolute address. Clear up to this? Right? Then we compare that absolute address to check whether we are crossing the boundary of the process or not, right? By using the comparator. If you are not crossing the boundary, that means you are pointing to the correct location, right? So now you can go to that address. Let us say this was 500, base was containing 500, relative was 50. So the absolute address will be 550, right? So you can point to this 550 address and get your data. Understood? This has to be done every time you encounter the logical address, right? Okay, good. Fine. So in case of paging, as I said, we again divide the main memory, right? But the size of division will be very small, right? So let us go through that. Main memory is partitioned into small fixed size chunks, right? Remember, the size of pages are again same. It is not like that you will be having one page of 4 MB, one page of 8 MB. It is not like that, right? It will be ideally in terms of KBs if it is a small scale OS, right? Okay. The other thing is process is also divided. We don't only divide the memory, we divide the process itself into same size chunks. So suppose I am dividing my main memory into 4 KB size, 4 KB partitions. So the process is also divided into 4 KB parts, right? Why it is required? Why do we need to divide the process? Because we have to load that process component into the 4 KB chunk, right? We have to load that process component into 4 KB chunk, and that is why we are going to do this, right? Let me go through an example so that you can understand, right? Suppose, okay, let me just cover the definitions first, then we'll go with the example. The chunks of memory are known as frames, right? Main memory partitions are known as what? Frames. The chunks of process are known as pages. The chunks of process, or you can say partitions of your process, are known as pages. I'll again repeat. Suppose you are dividing process into 4 KB parts. Process, remember, I'm not saying memory. Process into 4 KB parts. Each of the 4 KB part is known as what? Yes, it is known as page. You can imagine it is like a book. We are having a book. Consider book is equal to process, right? When you open the book, you turn one page. That means you are reading one part of the process. When you turn the second page, you are reading the second part of the process. Are you getting the analogy behind this? Right? Okay. Now, the memory space is also divided, or you can say main memory is also divided into same 4 KB size. I'm just saying 4 KB as an example, right? But that partition is known as what? Frames. Okay. So which we need to, or which component should be loaded into which other component? Pages have to be loaded into frames, or frames have to be loaded into pages? Pages. It is the process. It is the process that should be loaded into main memory. I hope you are following this. Yes, page size and frame size are same. That's correct. Yes. Right? Pages of process should be loaded into main memory frames. I'm going in detail. Clear with this statement? Pages of process are loaded into main memory frames. Okay? Let us see an example to make you clear. Okay. Is paging concept used to avoid reduce? Yes, yes, correct. We'll see that in the summary part. Was it? Yes. Okay. So this is the main memory that we are having. And suppose I have divided the main memory into 15 equal parts. I'm not saying what is the size, right? 15 equal parts are available. It is 0 to 14, right? And we call that as frames, right? Remember? That means we are having 15 frames available. Is that first image clear? We are having 15 frames available. Okay. Suppose you are loading one process, right? And that process is having size of 4 pages. That process is having size of 4 pages. Now entire memory is free. So I can load that process into the first 4 frames. Yes or no? 4 pages of the process are being loaded into 4 frames. Okay. Now, same process pages should be contiguous? No, not necessary. I'll be covering that example. Right? Not necessary. We should. That is the advantage of paging. Right? See, now we are loading B with 3 pages. So still I'm going in sequential manner because the addresses are available. Okay. That's why I'm going in sequential manner. Are you clear with the third part, third image? Again, I'm using the reverse approach. We are looking at the example first, then I'll go with the theory, right? So that you can map it out. Okay, fine. Process C requires 4 pages, right? Or it has to load 4 pages. So it is loaded over here. You can see over here, C0 to C3. Still we are having how many free frames? 4 free frames, right? We are still having 4 free frames. Now is the question. We require, or we have to bring another process that requires 5 free frames. Can we load that without swapping? Can we load that new process without swapping? No, right? So now it is up to the dispatcher again, right? Dispatcher is again going to come into picture. Which process to take out? Or in other words, this is also the area of replacement algorithm, right? We are going to study that later on in the virtual memory chapter, right? So replacement algorithm will decide which process you will take out, okay, and which process you will bring in. So suppose your OS decides that B was having only 3 pages, right? So it is the smallest process that we are selecting, okay? So for that case, we are having a hole over here and there is another hole over here. Now the advantage comes into picture. See, how we are loading D? D is requiring 5 pages. So 3 pages of D can be loaded over here. The remaining 2 pages can be loaded over here. Are you getting the advantage of paging? This was not possible in earlier case, right? So Vishnu, are you clear with that question? How stack is maintained? Yes, we are going to see the data structure that maintains this, right? We are going to look at that, right? B process is completed, or as we need space. Yes, it is not completed, right? It is just that your replacement algorithm has decided that you have to swap out B, right? It is not contiguous, that's correct. In case of fixed partitioning or even in case of dynamic partitioning, contiguity is required. Over here, contiguity is not required, and that is why paging is a very, very popular scheme, right? That is used nowadays, right? Understood the concept? All of you, right? Okay, defragmentation is required over here as well as, yes, that's correct. But the amount of defragmentation will be less because ideally it will be at the end, right? So the amount will be less, right? Yes, I agree that there will be internal fragmentation, but we will see where it is occurring, right? That we are going to see in detail. Every page should convert to physical address. So basically, whenever you encounter an instruction that is having logical address, you have to convert to physical address. That is the concept, right? Suppose you are having a jump instruction or jump if carry, jump if not carry kind of instruction, right? In that case, you have to do mapping, right? Otherwise, it is not required. Okay. Let us go to the theory now, right? So that we can understand the data structure part. Frame size is equal to the page size, right? Not the block size. Block is a different concept, right? Block is a different concept, but frame size is equal to page size. That's what we can imagine. And that is true for all the OS, right? That is true for all the operating systems. Okay. Let us go into the theory now. When a process is to be loaded in main memory, first we find the free frames, isn't it? That is what we need to do first. We find the free frames, and then wherever free frames are available, pages of the process will be loaded, right? I am saying wherever because it may be that you might be having two frames available in between, right? So you will load 2 pages over there. Remaining 3 pages will be loaded at the end, right? Contiguity is not required because we are having a data structure that maintains the information, and that is known as a page table. We'll see that very soon, right? Frames are basically partition of memory. That's correct. And pages are partition of process, right? If you understand, then there won't be any confusion, right? Yes. Okay. Now, to do this job, we have to maintain list of free frames. Yes or no? Obviously, we require a data structure that has to maintain free frames, right? So your OS maintains a separate data structure that is called free frame list. Free frame list, right? And in that, you will be maintaining the numbers of frames which are free, index numbers of the frames which are free. I'll show you that over here. This is the data structure, right? Frame number 13 and 14 are free. How to verify that? From here. Is it clear? Frame number 13 and 14 are free, right? And that is mapped in this free frame list, okay? So this is one data structure that is required by the OS. What is the other data structure? Let us see that, right? If contiguous frames are not available, then also new process can be loaded, right? But if you want to achieve this requirement, what do we need? Track. I need to maintain track of the allocation. How do we do that? Using a separate data structure to keep track of current allocation, right? Let us see what is that data structure. It is known as a page table, okay? Every process has one page table. Remember this thumb rules, right? You are going to use this in any competitive examinations, even somewhere in the interviews. If you are asked any question regarding OS, these are common topics from where the questions will be coming, right? How paging works, how segmentation works, right? Many companies ask this in interviews, right? So you should know this. So every process has one page table, right? Now what page table contains, right? So ideally what you should contain in the page table? Yes, it should contain where your pages are loaded, isn't it? It should contain where your pages are loaded. And where you load the pages? Where you load the pages? In frames, isn't it? So what do we need to maintain inside the page table? The index numbers of frames. Or you can say frame numbers, in other words, frame number. Got the concept? I'll show you the example also, right, to make it clear. Fine? Okay. Again, I'm repeating, every process has one page table, and page table entry contains frame location, where the page is stored. Okay, or in other words, frame number. If you want to write in one word, it is frame number. Okay, let us see. Process A's page table will look like this. Why it is having 4 entries? Because it is divided into 4 pages, right? Because it is divided into 4 pages. So I'm having 4 pages, okay? And where those frames are located, or sorry, where those pages are located, that is maintained over here, right? Page number 0 is stored at frame number 0. How to verify that? From here, right? This is your frame index, right? This is your frame index. Okay, are you getting the concept? Right? Okay, good. So 0, 1, 2, and 3, right? Why it is same on both the sides? Because it was the first process to be loaded. Otherwise, it will not be like that. Now, why process B's page table is empty? Can you give me the reason for this? Why process B's page table entry? Yes, it is swept out. It is swept out. So remember, page table is not deleted. Why? Even though the process is not in main memory, its page table still resides in main memory. Why so? Because process is not completed. That's correct, right? Process will come back again, right? And if you remove the process page table when the process is swept out, you have to create the page table once again, right? So rework has to be done. Okay. So to keep track, we keep all the page tables of all processes, right, in main memory. So if I'm having 10 processes in main memory, how many page tables I require? 10. And again, where they have to be maintained? In main memory again. So are you getting? We are again competing for main memory, right? Earlier we were discussing that main memory is required for processes and processes are competing, right? Now processes require additional memory for page tables, right? This is one of the reasons why RAMs are increasing, right? Because as the process size increases, what will be the effect on the page table? Suppose your process is 4 MB right now, it is becoming 16 MB suddenly due to the rise of your data. So as the process size increases, number of pages will increase. As number of pages increase, size of page table will increase, right? It is going to rise exponentially, right? So this is the reason why people are working on increasing the RAMs, right, from time to time, because main memory is having a lot of competition, right? Okay, if you use virtual memory, this problem can be reduced. We'll see that in the 8th chapter, right? Okay, let us look at process C, 7, 8, 9, 10. Can we verify that by looking at the figure? Right, let us look at that. 7, 8, 9, 10, is that correct? Right, for process C. Similarly, if you look at the process D, right, 4, 5, 6, and 11, 12, right? So 4, 5, 6 is over here and 11, 12 over here. So now I think you are able to understand why we are able to load the process into non-contiguous locations. Why? Because we are maintaining that record in a page table. Is that clear to all? Right? Okay, good. So this is about paging, right? And the basic concepts of paging. Still, we are going to look at some examples, right? Because in exams like GATE, you are asked numericals more often from this concept, right? So we'll look at some of the examples, right? Is it the reason for cheaper hardware? Yes, yes. One of the reasons you can say, right? Yes. Okay, now we are going to the example side. So let us discuss the concept first before we solve some examples. Instead of storing all addresses, why don't we store the start and end of all frames? Yes, but as we require every individual page's starting and ending location, right? That's why we need to maintain everything. Because see, we are going to divide the process into, let us say, 4 pages, right? So I should know where my first page is beginning, where my first page is ending. I should know where my second page is beginning, where my second page is, because it is possible that first page might be loaded in some other location and second page might be loaded in at the back end, isn't it? So that is why you have to maintain every page and its starting and ending.
The process is divided into 4 parts. Okay. So why don't we store the ranges of all those parts, the starting and ending address, the starting and ending of each range
Each
Why
range.
should we store all each and every?
Okay, see, if you store the ranges, that is one approach. And if you just store the frame numbers, that is the other approach, isn't it? So now we need to execute that and we need to compare, right? That is what can give us the outcome, right? Yes, that can be a valid approach. Agree with that. But when the paging was introduced, they came up with this simple division. That is, you maintain frame number, and actually this requires lesser memory, isn't it? You are maintaining just index. Index is just an integer, right? So this requires less memory. Yeah.
Suppose C process is, has index 1 to 3 and then 8 to 10.
Okay.
So rather than maintaining 1 to 3, 8 and 10, why don't we maintain 1, 3 and leave some memory and, or just a one chunk and 9 and 8 and 10?
Yes, yes. Okay, okay. So what Rishi is asking is we can still optimize this, right? Yes, I got your point. You can optimize this approach, but in that address translation again should not have any problem, right? Because if you are maintaining in that way, at the time of translation, right, you should be able to find your addresses, right, correctly. If with your theory, if you can prove that the address translation will not have any problem, then definitely it is a valid approach, right? So yes, we can think over that in detail, right? Yes, that's correct. Yes, in paging, priority applicable? No. See, basically, Urjit, we are having process divided into pages, right? So if your process is of high priority, right, then priority is applicable, definitely, right? But as far as the page divisions are concerned or loading is concerned, priority does not play a role over there, right? Are you getting this? Yes, okay. Because it is not contiguous, and again maintain the start and end pointer. Yes, yes.
Sir, can you go back to the figure one?
Yeah, yeah, sure, sure. Figure 1. This one?
Yes, sir.
Yes. Where is the doubt?
Sir, now if there is we have replaced the B process.
Yes, you replace the B process. Okay.
So why only B? Can't
Yeah,
we?
yeah. So
do,
that's what
with
I said.
C?
Yeah. I got your question. See, basically, we have not covered those algorithms because they are part of virtual memory chapter. We are going to use a concept called replacement algorithm over here. So the question, I think Urjit, you are speaking, right? Yes, okay. So Urjit has a question that why we are swapping out B only, right? So the answer to that is we have something called a replacement algorithm, right? Replacement algorithm are again divided into number of types, like you have a FIFO, last in first out, priority, right? There are so many algorithms we have. Based on that replacement policy, you decide which process to swap out, right? And then you already know which process you are going to bring in, isn't it? But what we need to decide, out of A, B, and C, which process we swap out. Okay, that is decided by page replacement algorithm. Why we are not covering that over here? Because before we go for that, virtual memory concept are required, right? So once we will study virtual memory, I'm going to cover those algorithms. Is that fine, Urjit?
Yes, sir. And sir,
Yes.
I have a second doubt
Yes.
that if here we are selecting the process which is the smallest one,
Okay.
means
Okay.
the B process is
Smallest size.
replaced and
Yes. Okay.
yes. So if I mix the concept of priority here
Yes.
and B have the highest priority, then
Yes. Then it won't be swept out. Definitely. See,
Okay.
priority scheduling. See, what Urjit is asking is if you are having that B is having highest priority, right? So then B won't be swept out, definitely, right? So replacement algorithm decides based on a criteria, like you have studied scheduling algorithms, right? First in, first out, the round robin and all those. Every method has a criteria, right? Similarly, there are 4 to 5 replacement algorithms which we are going to see, right? Every algorithm has a criteria, and based on that criteria, it decides which process to swap out. Is that fine, Urjit? Yes, and okay, another demand with paging. Yes, we are going to see demand paging and all those concepts later on, right? It is coming up, but first we need to cover this concept. Okay, now I'll take 1 more minute, then I'll stop. this after scheduling thing. Yes, this will be done after scheduling, right? Definitely, right? Okay, logical address is a pair. Every logical address or a relative address is a pair always, right? It contains a page number and an offset. Now, what is going to be offset over here? Suppose your process is divided into 4 pages, right? Now, in the first page, if I want to point to the 5th byte, understand my statement. In the first page, if I want to point to the 5th byte, right, what that 5 is called? 5 is the offset, exactly, right? And what is 0 over here, or what is 1 over here? Page number, isn't it? Are you getting this idea? Right? So page 1, offset 5. That is how we actually have to map. Okay. So now let us look at the mapping, then we will stop, right? In your main memory or in your process, which kind of address you will be having? You will be having the page number and its offset, right? That has to be converted to what? Frame number and offset, isn't it? Why we are going like this? What is the assumption behind this? What is the assumption behind this? Size of page and size of frame are same, isn't it? That is why we can convert this. Okay. So your page number and offset will be in logical form, right? That has to be converted into a physical address, and where the physical address is loaded? As frame, as a form of frame, right? Who does this? CPU hardware. So in next week, we'll take an example of this, and then we'll solve all these examples. Okay, and you can prepare for your gate if you are doing, right? Because many examples like this are being asked. Simple examples can give you 1 to 2 marks in gate, right? So we'll solve that. Okay, let us stop over here.